So we're quickly looking at isomers. It's just also organic molecules, but you need to know that there are actually three different types of isomerism that you can have in organic chemistry. So on page 714, you'll get the definition. It says an isomer is a compound having the same molecular formula, but with different structural formula. So molecular formula, you do know by now, is basically the simplest formula. So that would be the empirical formula of the isomer. So meaning that there would be 4 carbons and 10 hydrogens. So the easiest way that we could draw it is just to say 1, 2, 3, 4 carbons, and then you go and fill in the hydrogens in their positions. I'm not going to do that for this whole lesson because that will take us too long, but if you get asked to draw a molecule, please remember that you have to draw in all the hydrogens. You can't just leave those spaces empty. Sorry. So that would be 4 carbons would be bute, and that would be then butane. So that you should know by now. Then if we look at the first type of isomer that we get is called a chain isomer. Now if I look at that molecular formula, the C10, oh it was not 10, C4H10, I could draw that in different ways. So the first one that you had there already on the previous page, the name of this that we said already is going to be butane. Now what I could do is I can draw 3 of my carbons in a row like that, and then I can have the other carbon forming a chain. So I've now got an isomer with no chains, and then I've got an isomer with a chain, but they still have 4 carbons. And if you put in the hydrogens in the places that they belong, you will see that there are still going to be 10 hydrogens. So this is still C10H4. So they've got the same molecular formula. But if you now go and name this molecule, remember we always look for the longest chain first. So if you look here, that would be my longest chain. You could have gone in the other direction like this as well, but we're just using the straight one for now. So that would be 3 carbons, which would be propane, because there's only single bonds. But then this here becomes a group that's hanging on, so a side chain. So it will be 2-methyl propane. Couldn't be on anything else, so it's actually just methyl propane. So if you name the compound and it still has the same name, then you must realize that it actually isn't an isomer and it is the same molecule. Because if I did this, if I take this carbon and now think that I'm going to make a chain by doing this. So what I'm going to do is I'm going to say, okay, I'm going to put that extra carbon on this carbon here. I hope you can all see that you've actually just made the chain longer, and that what we now have is 4 carbons again, and again we have butane. So that would not be an isomer, it would just be the same molecule that we had before. So what you need to get from this is that chain isomers is an isomer that it's the same molecular structure, different structural formula, and what you then see is that, oh, now I'm taking everything away, but it doesn't matter. You can then see that this molecule has a different structural formula to this molecule here, and it's going to have a different name. Make sure that it has a different name, and therefore they are called chain isomers of each other. Molecules with the same molecular formula, different structural formula. Sorry, this is not going away. Then for positional isomers, we can use a molecule again. So let's say that is our molecule, and we have a haloalkane. So let's put our bromine there. So there's a bromine there, and if I name this, it will then be 2, because it's on the second carbon, bromo. And because there are 3 carbons, it's going to be propane. So 2-bromopropane. And then for a positional isomer, all that's going to happen is that this functional group must change positions. So instead of being on the second one, we are now going to move it to one of the others. So in this case, if we move it there, it will be on the first one. And if we move it there, it will be on the first one. Remember, we always start counting from where something is happening. So I could move it there and there, which means I then end up with still the same molecular formula, but instead of the bromine being in that position, we are now going to move the bromine to this position, which will make the molecule 1-bromopropane. But both of these molecules will have a molecular formula of C3. If you count the hydrogens, it must be double the amount of carbons, remember, but then and plus 2. So it will be 6 plus 2 is 8, but then one of their places is stolen by the bromine. So, or you can just go and count 1, 2, 3, 4, 5, 6, 7 hydrogens. So 7 Br. So this would be the molecular formula for both of them, but these will be the structural formula or names of the structural formula, and the names must be different. Now the last one, and you don't have to hear me cough again for today. The last one is a functional group isomer. What this means is that they have to have different functional groups. I'm hoping you're seeing that the names are according to what is different. Here, a chain isomer, the chains are different. Here, the positional isomer, the position of the functional group is different. And here, they actually have to have different functional groups. For us, there's actually only going to be 2 of these, and those are the esters and the carboxylic acids. The others are all going to be chain isomers or positional isomers. So if you look at something with a formula, let's say C2H4, I think this is the one in your book. Let me just quickly check. Yes, this is the one in your book. Now, if I'm drawing that, there's 2 ways I can draw that. So that's the molecular formula. I could have 2 carbons like this. Now I need 4 hydrogens. So this carbon could take 3 hydrogens. But then for a carboxylic acid, I will have a double O, double bonded O, and then remember it ends in an OH. So I have my 2 oxygens and I have my 4 hydrogens, because this will be a hydrogen and a hydrogen and a hydrogen. But this will be then the carboxylic acid. There are 2 carbons, 1, 2, so it will just be ethanoic acid. If I now change this and I want the O in a different place, so I need another functional group, the only other thing I can do with 2 O's in your syllabus is an ester. So I need to have my carbon, and it needs to be interrupted by an oxygen and then the other carbon. Now it doesn't matter, I can put the double O here, and then this one will just have an H, and then here I'll have my 3 H's. So if you look at those, this is now an ester because it's broken by that, the carbon chain is broken by this oxygen here. So an ester and a carboxylic acid will be functional group isomers of each other, because this will still be C2H4O. I'm just going to do one more of these because this is the one that you need to spot, and it's actually the easiest one because it's the only one with 2 O's. So let's say I had another carboxylic acid, so one with more carbons. So carboxylic acid, always a double O at the end with an OH ending the molecule. All of these spaces will just have hydrogen. Now if I want to make an ester out of that, so that is going to be C1, 2, 3, 4. You can count your hydrogens, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And then I've got 2 oxygens. So that is my formula. Now remember, that's not allowed to change. So if you're going to do an ester, you can have 3 carbons before you break it with an oxygen. You can have 2 carbons before you break it with an oxygen. It really does not matter. But then you must just make sure that when you're done with it, there are still 4 carbons. And you can also decide where you're going to put the double O. So you could put the double O on this carbon here, which means the main name of this will be according to the 3 here. So it will be methyl, because there's only 1 carbon here, and because there are 3 on this side, propanoate. So it will be methyl propanoate. If we look at the second one, let's put the double O there. Then you look at this is going to be the group hanging on, so it's ethyl, and because there's 2 carbons onto the double O, it's going to be ethyl ethanoate. So butanoic acid will be a functional group isomer of both these esters. And where these esters of each other, if you just look at the 2 esters, they will be positional isomers because the position just changed. The position of the functional group just changed. Okay, so that's isomers, and then you need to mark for today still the exercise 2, 3, and 4. So I'm going to put the memo for exercise 2, 3, and 4 on, and then you can mark your exercises, and we can then it's your Siyavula exercise.